Well, the agenda of this lecture is the characterization of minimizers or minimum points and saddle points with the help of the second order partial derivatives of a given function of several variables. So neatly the agenda is second order optimality or saddle point condition for a function of several variables.
If we revisit our last lecture's video, then we will observe that we have started our discussion in the topic of first order and second order characterization of a direction being descent. And with the help of the first order characterization of decency of a given direction D, we have identified a first order necessary condition for minimizer. And this condition was that at a point x bar, if a function f is having a local minimum and if the function f is known to be differentiable, then you should have the gradient value of the function f at the point x bar a null vector. However, this condition is just a necessary condition, it is not a sufficient condition, and towards that we have seen two examples. Those were function of one variable x cube. For function of two variables we have taken x1 square minus x2 square, this hyperboloid, and then later on we were trying to discuss the notion of saddle point. By a saddle point we mean a point in which a function f is having neither a local minimum nor a local maximum, and also saddle point must be a stationary point. And then the piano example was given, an interesting example on saddle point as well as an interesting example for which we have observed that the function f is having a local minimum along every possible direction emanated from the origin, but the function is not really having a local minimum at the point origin. This is due to the fact, you note that we always feel a function of two or more variables can decrease only on a straight line direction. It is not really the fact. For function of two variables, you can have a curvical path along which the function might get decreased. You can have a curvical path, and for those curvical path you may not have known exact expression to move along those curve. You may not have an expression of this curve, you may not have an expression of this curve, and therefore what's happened, if we just visit function of two variables along only on particular straight line directions, and if you finished visiting all particular straight line directions, those can be emanated from the given point x bar, and if you have found the function is having a local minimum along every possible direction, by that you cannot ensure that the function is really having a local minimum at the point x bar, because you can have a path, a curvical path along which function might not decreasing in nature, and therefore the function might be decreasing in nature along a particular straight line path, along every possible straight line path, but you have not visited the curvical paths which are also possible to be emanated from the given point x bar. And therefore this common perception that if a function f is having a local minimum along every possible direction emanated from x bar, then the function must be having a local minimum is not really true. Well, so anyway, so that we have seen with the example by given by piano, and now today we will continue our discussion with first order sufficient condition, or FOSC, that is a common abbreviation in any optimization book. Mostly you will see that these abbreviations are used. FONC for first order necessary condition, FOSC for first order sufficient condition, SOSC for second order sufficient condition, and so on. So in today's class we will start our discussion in the topic of first order sufficient condition for a minimizer. Then second order necessary and as well sufficient condition for minimizer will be discussed. Later on, towards the end of the class, we will try to discuss second order sufficient condition for saddle point. In between, a point that I have missed to prove in convex optimization problem, in convex functions rather. where although I have mentioned it several times, I have spoken out, but I did not prove, somehow it missed out, that if a function which is known to be convex is having a local minimum at the point x bar, then the point x bar must be a global minimum, and that is the fascinating result in convex functions. And that's why, due to this particular thing, and as well that any stationary point is a global minimum, due to these two particular facts about convex function, possibly convex optimization problem is richer. And that's why today you have several platforms, computational platforms, by which you will be able to solve a convex optimization problem efficiently. And this is so efficient, it is said by Stephen Boyd, who mentioned in his book Convex Optimization, that convex optimization techniques are now going to be almost reliable technology. Which are reliable technology? By reliable technology, what do you mean? We know that if we just take example of a simple calculator, in the simple calculator you can just give two numbers and multiply, and it gives an output, and which is a perfect value of the product of two numbers that you give. I am taking here just one instance of product. Several other calculation also you can reliably do in computer, in calculator. But what is hidden in calculator is a program, and that program is eventually coming from certain amount of rigorous mathematics. And then mathematics are being programmed, and those programs or those methods are so efficient that that can be reliable technology. By reliable technology, what do you mean? That those programs can be just plugged into a system, and you just forget about all the mathematics, forget about all the programs that is being plugged in your system, that is being hidden into in your system, in your calculator. And afterward you just play with any numbers, and you get the output as the perfect value of your operation. And therefore whatsoever technology is being used in calculator is a reliable technology. Similarly, methods to solve convex optimization problem in today is going almost a reliable technology, so said by Stephen Boyd, one of the most cited convex analyst, convex optimizer. Anyway, so convex optimization is possibly reached due to two particular properties. Those are any local minimum is a global minimum, and much deeper, any stationary point is also a global minimum for a convex function. Today we'll prove both the facts in between. Anyway, so in between our agenda that we have given here, three agenda in today's class. Let's start our discussion in the topic of first order sufficient condition. In first order sufficient condition, we have the following result. First order sufficient condition of local, or rather it is global also, of minimizer. It is that if your objective function is convex, so here C is a non-empty convex subset of the n-dimensional Euclidean space. Non-empty open convex set, and we let this, and also we let that x bar is a stationary point. Gradient of f x bar is equal to null for some x bar belonging to C. Then x bar is a global minimizer of f on the set C. And why this is happening to be true? This is due to the first order characterization of convex functions. As you by now know that if a function f is convex and if it is differentiable, then you know the tangent line or the tangent plane or the tangent hyperplane at any point is supporting hyperplane or a global lower estimate for the given convex function. Fine. And therefore, if we in particular choose the point x bar, and at the point x bar you take the tangent hyperplane that supports, and obviously you have this inequality fx greater than equals to the inequality that I have written here. So as you have f is convex and differentiable on C, you have this, and this essentially implies your result that this is greater than equals to fx bar, right? Because gradient of fx bar is equal to the null vector, and once you have this, this implies the point x bar is a global minimum. Fine. And we note that it may be tempting to think that if we have the directional derivative of the function f at the point x bar along the direction x minus x bar is greater than equals to 0 for all x belonging to
Rn, then the function f has a global minimum at x bar. But this is true only for a convex function. For a non-convex function, this directional derivative is greater than equals to 0 does not necessarily imply that the point x bar is a global minimum of the function f.
what does this inequality says? It says along every possible direction, whatsoever direction you can think of, along every possible direction emanated from x bar, whatsoever direction you can think of, along that direction you have the directional derivative greater than equals to 0. This implies that there is no descent direction of the function. That is, gradient of f x bar transpose uh, d is not less than 0 for all d belonging to Rn. What does this inequality says? It says you don't have any direction d for which you can realize that f is decreasing in nature. So there is no descent direction. The condition that the function f does not have any descent direction does not necessarily imply that the function f is having a local minimum at the point x bar. This is in the same line that I have started my class, that you might have a curvical path, along which the function might degrade. It's not that, and therefore that will stop us to realize the point x bar a local minimum. Consider this, and then you just check that this condition is satisfied. The inequality that I have assumed here is satisfied at the point 0, but the point x bar is not really a local minimum. Fine. So now next, let me move ahead to the second order necessary and sufficient optimality condition. For this, you have the following result. It says that let f be twice differentiable, because you are putting second order condition. You are assuming that f is twice differentiable function at x bar, and you have x bar is a local minimum of, fine, then necessarily the gradient must be vanishing, that we have already seen, and also the Hessian of the function at the point x bar is positive semi-definite. Let us try to prove this result, because this result we will use most often later days. So now the first necessary condition, this is already proved, that gradient of fx bar is equal to 0 is proved. We are skipping this, and for hx bar to be positive semi-definite, how do we prove this? To prove this, so we let us consider any direction d, and what do we have to prove is that required to prove d transpose the Hessian, any notation you use, either nebula square, fx bar or hx bar, d is greater than equals to 0. That is what we have to prove. And as d is arbitrarily chosen, there is no restriction on d being put, and therefore once you can prove this is greater than 0, that will prove that well your hx bar is positive semi-definite. Now from twice differentiability of the function f by Taylor's theorem, what we have is plus small o of lambda d norm square, or rather it is lambda square. Fine. Now as your x bar is a local mean, therefore there exists a delta greater than 0 such that you have f of x bar plus lambda d is greater than equals to f of x bar for all lambda, such that lambda is in between 0 to delta. Okay, and then this 1 and 2 will imply that you note that here this gradient of fx bar is a null vector, so second term gets vanished, and accordingly you have then from 1 and 2 that lambda square by 2 d transpose Hessian at the point x bar d plus small o of lambda square is greater than equals to 0, and for all lambda such that 0 less than lambda less than delta, right? Now as small o of lambda square is such a function that if I divide by lambda square and taking lambda tends to 0 plus, you have d transpose Hessian fx bar d is greater than equals to 0. Therefore your result is proved. However, this is really necessary condition for optimality. This is not a sufficient condition of optimality. To establish this, let us consider one example to check that the condition is really a necessary condition. For this, let me consider one example. For example, consider the function if x1 x2 is equal to, let me consider a function x1 square minus x2 cube, and x bar is equal to the null vector. Fine. For this function, you can check that this is a saddle point. X bar is a saddle point, and Hessian is positive semi-definite, and gradient is a null vector. You can check that, and I'm putting this as a homework. You just check this, verify this. Now, what can be then a sufficient condition of optimality? For this, you require positive definiteness of the Hessian, and that is our second order sufficient condition. That is the following. This states that let A be twice differentiable and gradient of f at x bar is the null vector and the Hessian is positive definite. Then x bar is a strict local minimizer of. Proof will be as follows. In the proof, we require a result from matrix analysis. That is the following result. where lambda mean and lambda max are minimum most and maximum most eigenvalues respectively of the matrix A. Let me just move ahead with the proof. How do we prove it? For the proof, we know that since f is twice differentiable, we must have a neighborhood, say b delta of x bar, such that where the Taylor's theorem can be applied. And this is true for every x in the delta neighborhood. Fine. And once you have this, then we know that we can write it as here this term is equal to 0. This term is vanishing, and therefore you will have here and this is valid for every x belonging to delta neighborhood of the x bar. Fine. Now we'll apply this result, the result that I have mentioned for a symmetric matrix. Here we note that we can write as this is a symmetric matrix and its eigenvalues are all 2 times the eigenvalues of the Hessian matrix, right? And therefore you have here f of x bar plus 1/4 of lambda mean norm of x minus x bar square of it. Fine. Where lambda mean is the minimum most eigenvalue of Hessian for all x belonging to B delta x bar. Fine. And as the Hessian is positive definite, therefore lambda mean is also positive, right? Because for a positive definite matrix, all the eigenvalues are all positive. And therefore, then what we have? We have this, that this is strictly greater than f of x bar as limit x tends to x bar small o of norm of x minus x bar square of it divided by x bar square is equal to 0. Fine. And due to this limit is equal to 0, then this delta neighborhood might get lessened, means might get shrunk, and therefore this has to happen for all x belonging to some delta naught of x bar with some delta naught that might be smaller than delta. Fine. That means x bar is a strictly local minimum, strictly local mean of. Fine. Now let me now mention a sufficient condition for saddle point, and afterwards we'll prove that a local minimum for a convex function must be a global minimum. Sufficient condition of saddle point. I note that once Hessian matrix is positive definite, then it ensures the strictly local minimality. And if the Hessian matrix is positive definite, obviously together with the point x bar is a stationary point. That means gradient of f at x bar is equal to null, and Hessian matrix is negative definite, then that will imply x bar a local maximum. So local maximum is related to negative definiteness of the Hessian. Local minimum is related to positive definiteness of the Hessian, and saddle point is related to neither of them. By neither of them, obviously, if the point x bar is such that it is a stationary point and the Hessian matrix at the point x bar is indefinite, then the point x bar must be a saddle point. Let me just state out, I will not prove, and for the proof I will refer you a particular book. So let f be twice differentiable in some neighborhood of x bar and second order partial derivatives of f are continuous at x bar, where x bar is a stationary point of then if the Hessian is indefinite, then x bar is a saddle. Now for the proof you can visit a very classical book. Well, so this ends of second order conditions for optimality as well as for saddle point. Now next let me prove the most fascinating result, although I should have proved this result earlier when I was discussing about convex function, I have missed somehow. This result is the important result that any local minimum is a global mean of a convex function. To be precise, that is, it says that if x bar is a local minimum of f which is known to be convex, then x bar is a global minimizer. This result is eventually true even if you restrict the function f on any given convex set. Fine. Let me prove it. Here you note that we have not assumed the function f to be differentiable. It is any convex function, even non-smooth, which is not differentiable. For that also this result is true. Anyway, so let me just prove it. The proof will be by the method of contradiction. So let's suppose, if possible, let x bar is not a global minimum. If this is so, then there exists at least one point, let's suppose x cap, such that the function value at x cap is smaller than the function value at x bar, right? So here let's suppose I have the point x bar and I have the point x cap, let's suppose here. Fine. Now as it is known that the function is having a local minimum at the point x bar, therefore there exists a local neighborhood of the point x bar in which the function value is minimum most at the point x bar, right? So let's suppose this is my delta neighborhood of the point x bar. Okay, this is my delta neighborhood, and in this delta neighborhood, as x bar is a local minimum, because that is the definition of local minimality of the point x bar, right? And here once you have this, then you note that if we now consider this direction, that x bar to the point x cap, you consider this direction, and this direction must be having a small amount of segment starting from x bar which must be lying inside this delta neighborhood. It's not that this much amount of length is inside the delta neighborhood, and that will give us a contradiction. How is it? It is really the following. You note that any point in this line can be presented by x bar plus alpha times x cap minus x bar, right? We can write in this way, and uh, this implies that there exists an epsilon greater than 0, epsilon amount of length. This epsilon amount of length you have at least, such that f of x bar plus alpha times x cap minus x bar, such that this point is belonging to the B delta neighborhood of x bar. Now can you precisely present an expression for this epsilon? Try a little. So at least an amount of a continuous amount of length for this alpha. There exists one epsilon such that for all alpha in between 0 to epsilon, you have that f of x is greater than f of x bar, right? For all alpha such that this. Can you be able to find this epsilon? This epsilon you can, let me construct. You can take this delta divided by x minus x cap minus x bar. Well, norm of the distance. If you take, then you know that this point is obviously is belonging to b delta of x bar. You check this. Fine. Then this implies what? This implies you have f of x bar is less than f of alpha times x cap plus 1 minus alpha times x bar. And this is true for every alpha, for all alpha such that 0 less than alpha less than epsilon, right? And as the function f is known to be convex, therefore this is less than alpha times fx cap plus 1 minus alpha times fx bar, right? Then you note that you have assumed that fx cap is less than fx bar, and therefore this is alpha times f of x bar plus 1 minus alpha times f of x. And this is what? This is your f of x bar. And it is contradictory that f of x bar is less than f of x bar. That is not valid, right? And therefore assumption is not valid that the point x bar is not a global minimum, is not valid, and therefore x bar is a global minimum. And this proved the result that any local minimum for a convex function must be a global minimum. Fine. Well, so this ends up the section for unconstrained optimization, at least theory. And several methods are going to come. And now to develop the method, you know, broadly to reach an optimum, although I have mentioned this in the very beginning class, that you start the methods they do start with an initial point x naught, then they move along a descent direction d naught say, and an amount of length, let's suppose alpha naught amount of length. So they reach at the point x1, and x1 is given by x naught plus alpha naught times d naught. Fine. And at this point they reach, then again they find a descent direction and they move along the direction, let's suppose this is a descent direction d1, and they move an amount of alpha 1 length and then reach at the point x2. And in this way, broadly optimization algorithms, they degrade the function values, and ultimately they reach at a point at which at least you realize that grad of f at the reached point, let's suppose xk, is equal to 0, and it is not precisely xk, a limit k tends to infinity. So once this sequence moves to this xk sequence generated by this way, that by this generic um, equation xk plus 1 is equal to xk plus alpha k times a descent direction dk. By following this sequence, if this sequence is converging, and mostly we'll see that they are converging to this equality, and by that if this sequence is converging to x bar, you will realize that mostly gradient of fx bar is equal to 0, and hence x bar is possibly a local minimum. Then later on you have to check with the second order condition that it is really a local minimum. And we note that what happens in every movement from xk to xk plus 1, from consecutive form from one point xk to, if you want to move to xk plus 1, then you are minimizing the function along a descent direction. And you note that a function along a particular direction, whatsoever the number of variable of the function, that reduces to a function of one variable. That is precisely phi lambda function. That is your f of at the kth iteration f of xk plus lambda times dk, right? And therefore we need to have efficient algorithm to find a minimum for function of one variable. And as you are trying to minimizing the function f along a particular direction or a particular line, identification of a local minimum along a particular direction is usually called as a line search method. Now slowly we are moving towards algorithmic development of optimization theories. So several methods will be discussed to identify local minimizer of a given function of several variables. And towards this, mostly this sequence will be followed: xk plus 1 equal to xk plus alpha k dk. And to identify consecutive iterative points, what we have to find is a local minimizer along a particular line, along a particular direction of the function f. And this line search algorithm then has to be talked, which are essentially algorithms to find minimum, local minimum for a function of one variable. We'll discuss in detail in the lecture of line search. But before line search, at first, in the next lecture, I will try to discuss general aspect of optimization algorithms. This is all about today's lecture. Well, thank you all for your kind presence.